Okay, we'll be looking at acids and bases today. In yesterday's lesson we looked at chemical energy changes, so it's being uploaded now, so it should be on YouTube if you guys wanted to go watch that. And I'll add it to the course in the course. If you look at where the prelim module is, right underneath the prelim module there's a discussion class module. So if you open that, all the videos are in order there that I've been doing for the last 2 weeks, except for Monday's lesson, which I couldn't record. We didn't have electricity, so but the rest should all be there. Okay, so acids and bases. Okay, so we have an intuitive idea of acids. We think of acids as something that's corrosive, and meaning that they're dangerous. Usually in our mind, they're dangerous and poisonous. So there is, however, a more formal definition, and there's two definitions that we're going to look at. Let's get there. We've got Arrhenius. I don't remember how to spell his name. R-E-I-U-S. Arrhenius. Arrhenius defined, was a double S, defined an acid as as ionizes, or how did he say it? He said donating releasing an H plus ion into an aqueous solution. Okay, so what happens when we dissolve? Remember when we did compounds that had ionic bonds? An ionic bond is a bond where one of the elements, for example hydrogen, donates an electron, and so he becomes positive, and he donates it to, and because he donates and becomes positive, he becomes a cation. And another one, for example chlorine, maybe he wants an extra electron so that he can fill up his energy level, so he takes that electron, he becomes negative, and now they exist as ions. And because they exist as ions, there is an attractive force between them, okay, and that causes the two, because one is a positive and one's a negative, they're attracted to one another, and they form a hydrochloric acid molecule. Now when we dissolve compounds into solutions, these molecules, these ions, gets released in a sense. They're free to move around much easier. Now they're still attracted to one another, so they're still close to one another, and so, but they're more fluid. They can, because remember, when most of the time when we have ionized reactions, they're ionic bonds, which means they got very strong forces, and as a result of those strong forces, they are solids. Okay. Now, as a solid, they stuck together. They're not ionized, but in other words, they can't freely move. But the moment I dissolve it into water, then these ions can move about more and easily be transferred to other molecules. So an acid is something that will release an H plus ion into an aqueous solution, while a base will release an OH minus ion, or OH minus ion, that's fine. We could, however, if our aqueous solution was water, H2O, then what will happen is this H plus will be attracted to the water, or will get stuck to the water and produce an H3O plus. So H2O has a zero charge. It doesn't have any charge because it's neutral. So if the hydrogen ion now attaches itself to the water molecule, it creates this ion. Hydronium, that's it. It's called the hydronium ion. Okay, so you can either think of Irenaeus as saying it's something that donates an H plus ion, or not donates, releases an H plus ion, or it releases hydronium ions in aqueous solutions. Okay, then a base releases the hydroxide ion. Okay, not an or in there. So an example of that would be hydroxide is an anion, and he will usually be connected to a cation, which is one of the first two columns usually in our periodic table. So this is a very strong base. We'll look at the definition of strong and weak bases just now. So, but here you can see that we've got sodium that's in column 1. Okay, so he will have a 1 positive charge giving away his electron, and he gives it to hydroxide, which becomes then 1 negative. Okay, so what would happen if we have water? Let me actually just first give you the Bronsted, just like that, Bronsted-Lowry definition of an acid and a base is that an acid donates a proton. Now, why is that very similar? You'll remember protons are fixed. You can't take a proton out of a nucleus. Okay? So how do you donate a proton, a single proton? The only way to do that is to give an atom that only contains a single proton, and that's hydrogen. So a Bronsted-Lowry, the way that he can donate a proton is by giving a hydrogen ion. Okay, so by giving it a hydrogen ion, hydrogen has 1 proton, 1 electron. But hydrogen ion has given away his electron, so he's only a proton now. He doesn't even have a neutron. So a single proton all by himself would just be a hydrogen ion. Okay, so a base is then defined as receiving a proton. So look what would happen if we take a few acids, and for example a very strong acid would be hydrochloric acid. Okay. If I were to take hydrochloric acid and I dissolve it into water, H2O, then we say that when something is dissolved into water and it breaks up into ions, we call it ionizing. So it ionizes, the hydrogen gets donated to the water to produce H3O+, that's the 1 ion, and the other ion that remains is chlorine. So in there is floating negative chlorine ions. Does that make sense? Okay, now we can look at what is called Bronsted-Lowry conjugate pairs. Okay. What that means is that on this side, something is donating ions and something is receiving ions. So if you look at this one donated, he's the one that donated the hydrogen. Do you see? Because here we have hydrochloric acid, yet we just have chlorine, so the hydrogen is missing, which means he is the one that donated. So he is the Bronsted-Lowry base, acid, because he donated it. And now who received it? Okay, this one received it. He used to be H2O, but now he's H3O. So this is the Bronsted-Lowry base. So these two are what we call conjugate pairs, acid-base pairs. Does that make sense? Okay. If we look at something like sodium hydroxide plus water, that produces, okay, Bronsted-Lowry base. I'm not going to use this one. If we look at ammonia plus water, this is a Bronsted base because it produces NH4 plus OH ions. Okay, notice how the ammonium used to be just NH3, but it becomes NH4. Okay, so this is the base. You see, because he got an extra, he's the conjugate base because he got that extra, is it? Yes. And then this one is the acid. Why is this one the acid? Because he used to be H2O, he used to have two hydrogens, and eventually he just has one hydrogen. So he's donated his proton, and he's donated it to the Bronsted-Lowry Base.
Got the negative one as well.
Yes, the OH.
Yes.
Yeah. Yeah. No, there isn't a thing like OH. There is, for example, something like SO3. That is a compound, but there's also an SO3 2 negative. Okay, so there is a distinction, but there isn't something like OH. So there is only OH negative. Okay. Let's move on to when is something a strong base or when is something a weak base. Okay, so a strong base or a strong acid, let's start with a strong acid. A strong acid is something that ionizes completely. That means if, or almost this, we can also say dissociate.
That's for acids.
Yeah, this is
for bases, because bases dissociate and acids ionizes, isn't it?
Okay, so what would happen with an acid if we put it in water is if we have H. Let's take another strong acid, H2SO4. Okay, hydrosulfuric acid or sulfuric acid. It ionizes in water into hydrogen H plus sulfuric acid SO4 2 negative. So two of these, one of those. Okay. The problem is because they are ions, they can come back together and form sulfuric acid again. You see? So because of this reverse reaction, it might be that some of the substance is still hydrosulfuric acid, the rest of the substance is ions, okay, when it's in the water. But a strong acid, and because it's a reversible reaction, we have equilibrium. At some point, the forward reaction and the reverse reaction has reached the same reaction rate. So now we have in our reaction vessel, in our water, there's now the ions, and then along somewhere we also have sulfuric acid molecules. Okay, a certain percentage of that is going to be hydrosulfuric acid, certain percentage is going to be ions. because it's a reversible reaction. Now, until that percentage remains fixed, the reaction is going back and forth until it reaches the equilibrium position. Does that make sense? Now, for strong acids, that equilibrium is to the far right, which means almost all of the substance is ions. There is very, very little to almost no sulfuric acid if it's a strong acid.
So when you say ions, you mean the hydronium?
Yeah, it's either hydronium or it's, I prefer to just talk about hydrogen ions, because that doesn't complicate the matter, okay? But whether I say, if we're talking about acids, whether I say hydrogen ions, remember the hydrogen ion attaches to a water molecule, then becomes hydronium, okay? So whether I talk about it has donated a hydrogen or hydronium, I'm saying the same thing. Because I'm donating it in water. If I'm donating hydrogen into water, I'm creating hydronium ions. Does that make sense? But I prefer to stick to this just for the explanation's sake. Okay, so now when we have this dissociation, understand now that in this vessel, if it's a strong acid, there is very little hydrosulfuric molecules, okay, attached molecules that form, these have been released, and the ions itself are now floating around in here. Okay, now what will cause this ionization process to happen very very well? What will allow this molecule to dissociate well? And that has got to do with how able is, because it's always an H plus, how able is the, so this is the cation, and then it's always connected to an anion, and that will make an acid. Now, how able is the anion to take away the electron? Not how much he wants it, but how able is he to take away the electron from hydrogen? Because if he can take it away from hydrogen, okay, he can give hydrogen off very easily. Does that make sense? It doesn't make sense. So remember, we have hydrogen has a electron, and he either wants another electron so he can fill up his energy level, or he wants to give it away so that he can at least have no extra valence electrons, okay? Which, if he does give it away, he becomes H plus. But he doesn't necessarily just want to give away. Like, his electronegativity is 2.2. Remember, we look at the electronegativity. 2.2 means it's roughly halfway between having a strong desire to give it away and having a strong desire to receive it. Okay, so he's halfway. So the question is, how able is the anion? In other words, who is trying to take it from him? Okay, now the one with the strongest desire, according to our periodic table, the strongest desire, look there, electronegativity is a measure of the desire for electrons. Who's got the strongest desire for electrons?
In the whole periodic table?
Yeah.
In the whole.
Yeah. Come on now. It's fluorine. Okay. Fluorine has a very strong desire. As a matter of fact, the strongest desires are fluorine, then oxygen, then chlorine, then bromine, and nitrogen, then bromine, then sulfur, then carbon. Okay, do you see these ones here? This little triangle up here has got the highest desire for electrons. Problem is, it doesn't matter how much I want something from someone else. If I'm not big enough, I'm not going to be able to get it. Understand? I also need to be big. So even though fluorine has a very strong desire, he's not big enough to kind of take it. So I don't know exactly how it works, but that's how it makes sense to me in a sense. So we have fluorine. Notice that the size of an electron, of an atom, depends on the size of his electron cloud. Remember, the electron cloud is the one that has the size, the nucleus is the one that has the mass. Okay, so the bigger the electron cloud, the bigger the atom. So fluorine, for example, only has 9 electrons, which means he has one energy level with 2 in, and an outside energy level with 7 in. He wants 8 in there. That's why he desires it so badly. And he only has few. That's why he's even got a bigger desire than the others, because he has few. But because he has few, it is a small molecule, a very small molecule. Okay? He only has 2 energy levels. So he doesn't have enough energy to attract to take away the electron on offer from hydrogen. It's very easy from these ones, from lithium, and so because they want to give these away. You see, lithium has a desire of 1.0, francium of 0.1. They don't want their electron badly, so they can easily give it away. Okay, but for hydrogen, he still wants to keep on to his a little bit. So fluorine is not big enough, strong enough to give it away. So fluorine, for example, is a weak acid, because there's now 2 factors that we have to look at. We're looking at a high desire for electrons, which is electronegativity, and we want to look at the size of the electron, a large size. That's now for the anion. So let's look at who's next. Sorry. Okay. The next desire, higher desire, is oxygen. He's 3.5. His desire. So he's got a lower desire. He's got a lower desire than fluorine. How many electrons does he have? 8. So in terms of his size, do you think he's bigger or smaller than fluorine? Smaller. So if we have fluorine was H plus and F minus to produce hydrofluoric acid. Now I want to know, does it ionize well? Well, it doesn't ionize well because fluorine is not strong enough to take the electron and just donate hydrogen away. Does that make sense? Now we're looking at water. At H and O. So how do we know what is this charge up here? You can tell me, how do I know what that charge is? How do I know this is O to the power of 2 negative? Oh, guys. What does that 2 negative mean? It gained 2 electrons. Why would it want to gain 2 electrons?
Because it has 6 electrons.
Sorry?
It has 6 electrons. It needs 2 in order to accomplish the objective.
Okay, so how do you know it has 6? Because it's in group 6. So how do we know that oxygen is 2 negative? We look here and we see, well, he needs 2 more. He's in group 6, he wants 8. So he needs 2 more. Okay? So if oxygen and hydrogen bonds together, we will need 2 hydrogens, because hydrogen can only provide 1 electron at a time. So we need 2 hydrogens for every 1 oxygen. Okay? So now the question is, how well does water ionize into these two? Okay, now water wouldn't ionize into this very well at all. Okay, we see why, because if we look at the table, we're asking ourselves the question, how likely is oxygen going to be to steal that electron from hydrogen? Well, he's got a lower desire than fluorine, and he's smaller than fluorine because he's got fewer electrons, and electrons is what gives the size, because the electrons is on the outside. So he's got fewer electrons, he's got a lower desire. He still has a very high desire for those electrons, but he's just not strong enough. So rather what they would do when oxygen and hydrogen combine is they would form covalent bonds. They would share those electrons. Okay, so water actually doesn't ionize into this, rather water ionizes into H3O plus O, sorry, not H3O, in H positive and OH. Water would ionize into these two. And you can see, in this case, water is both an acid and a base, because water donates H plus and water donates OH. You see? So when water is both an acid and a base, and that is why when we get to pH, I'll explain that. That's why the pH of water is it's not that the pH of water is 7. The pH of water is the standard. And the standard, when we go and measure the pH of water, we find that the standard is 7. The pH of water is 7, and that becomes the standard. And anything more than that produces more of the one, and anything less than that, more of the other. Okay? So that is now, if we check the hydrogen and oxygen, let's see hydrogen and nitrogen. Hydrogen and nitrogen, wait, I'm losing my place here. Hydrogen and nitrogen would be NH4. NH4. NH4 would be 4 hydrogens, this was 2 hydrogens, 4 hydrogens and it's not 4, it's 3, sorry. This is the compound, NH3, ammonia. Is ammonia a strong acid? In other words, would it donate hydrogens and nitrogens? Nitrogen is 3 minus. Why is it 3 minus? It needs 3. It needs 3. 1, 2, 3 to get to neon. Okay? So, and 3 what? 3 electrons. And that's why it's negative. Okay? So, would it dissociate? Would nitrogen be able to get hydrogens? Well, if we look once again at our table, nitrogen is again, he only has 7 electrons. So he's even smaller. And even though he still has a large electronegativity, okay, he only has 7 electrons. And so he actually does worse. He actually doesn't donate hydrogens. He ends up becoming a base even. That's how bad he is. He ends up becoming an electron, a proton receiver. He rather receives more protons than even giving it away. Okay. Next up is, let's go to the next high one. So all I'm doing is I'm following the electronegativity. I went from the highest one to the next lower one. But as I'm going in this direction, the size of my electron is decreasing. As I go down, however, my size of the electron is increasing. Sorry, not the electron, the atom. So if I go one down, okay, I see this is a 3 is still a high electron negativity. Chlorine really wants electrons badly. And not just that, he has 17 electrons. He's got 3 energy levels, sorry. Energy level, because he's in row 1, 2, 3. So as an atom, he has high energy. Does that make sense? He's a large atom, he's got electrons in high energy levels, okay? Which means chlorine is actually the strongest acid. Because not just does he have a strong desire for acid, he is relatively a large molecule because he has a lot of electrons. Does that make sense? The next strong acid, again, as I'm going in this direction to the left, the size of my molecule decreases as well as the desire for electrons. While if I go down, yes, my desire for electrons decrease, but my size increases. So hydrochloric acid is one of the strongest because it's got high electronegativity, a big molecule. Hydrobromic acid is high electronegativity, fairly high, 2.8, and it is even a larger molecule. Okay. But as I go down, here you can see 2.5. I'm comparing that to 2.1. So 2.5 is now coming close to 2.1. So the difference between their desire for electrons is getting lower. So by the time we get here, it stops being strong acids anymore. Okay, so far, some of the strong acids that we've looked at was the hydrochloric acid is strong, hydrobromic acid is strong, and hydroiodic acid is also strong. Again, it all depends on their electronegativity and their desire for the size of the molecule. But that's not the only time that we have ions, anions. We could also, we just now looked at all of group 7, okay, where fluorine was excluded because it was a small molecule. So all of group 7 elements, especially the middle 3, they form strong acids. Again, what does that mean if I form a strong acid? Is that when I put it in water, we all of a sudden have the ability to get rid of this hydrogen ion. Okay, I can now take it and release that hydrogen ion into the water, and rather let it connect to the water than to the anion. Does that make sense? So when I do that, when I dissociate, the stronger ability that I have to do that, the more I will dissociate. And so one of the strongest ones is hydrochloric acid. Okay, next hydrobromic acid, next hydroiodic acid. But now it's not necessarily that my ion is one of those group 7. I could also have these ions. Okay, they're called polyatomic. There's more than one atom in that ion. Poly means many, atomic. So I have these ones, and you guys are going to have to go watch the video to see. Okay, so this is a 1 negative. Okay, here is just some of the common ions that we're going to use. So you might recall the T, there's the T41. You guys remember that? Okay, so in the T41 table we have the T for the polyatomic ions. We have the T. Okay, so T41, and there's the T, there's a 4, and there's the 1. T means that this element is bonded to 3 oxygens. The 4, it's bonded to 4 oxygens, and the 3 and the 1 here, because there's 3 in this 1. This is also bonded to 3 oxygens. That would be the standard polyatomic ion. So for example, phosphor, if it's bonded to oxygen, it is PO4 because he bonds to 4 oxygens. He's in the 4. And then the charge is fairly simple because we have phosphor is 1, 2, he needs 3, so he has a reactive, yeah. So phosphor has 3 extra electrons. Oxygen has 2 extra electrons, but there's 4 of them. So we have 4 times, so in total, how many extra electrons do we have? We have 4 times 2 is 8, 11 extra electrons. So if we take away 8, because 8 electrons will fill up a new energy level. So if we take away 8 electrons, minus 8 electrons, we're left with 3 electrons. So phosphor will have a 3 negative charge. Okay. This one, so, and that would be phosphate. That one would be phosphate. If we add an oxygen, it wouldn't change the electronegativity of this one. The charge of that one wouldn't change it, but the name will change to perphosphate. Perphosphate. Okay. And if we take away one, so PO3, it will still have the same charge once again, and it will be called, it will now be called phosphite. I take one away. So the same with chlorine, it would be chlorate, chlorate, chlorite, perchlorate, perchlorate. Okay, but chlorate is in, chlorine is in the, so there's the T41, he's in the 3. So chlorate will have 3 oxygens, so he will be ClO3. And again we do the same thing. Chlorate has a 1 negative charge, there's 3 oxygens, which is 6 negatives, so in total we have a 7 negative charge. That doesn't work out. Yeah, so in other words, in order to get to 8, I'll have to get another electron, which will give me once again a negative 1 charge if I have an extra electron, or 1 negative charge if I get my extra electron. Okay, so that's just more or less what these are called, the polyatomic ions. Now, if I talk about sulfuric acid, I'm talking about the sulfate ion with hydrogen. Okay, if I'm talking about phosphoric acid, I'm talking about the phosphate ion. If I'm talking about chloric acid, is it CHCl? No. If I'm talking about chloric acid, I'm talking about the chlorate ion. Okay? So if I am talking about perchloric acid, I am talking about the chlorate hydrogen with the chlorate ion, which is ClO3, but per means 1 extra oxygen. So this is perchloric acid. Okay. If I take away 1, the N become sulfurous. It gets an "-ose at the end. Okay, so I'm not gonna, that's also in the video, so I've taught that before. Okay, I just want to show you how does that affect the strength of an acid. Is that, first of all, it still depends on the desire that these elements have to get electrons. Okay, so the electronegativity, but we don't have electronegativity for polyatomic ions. Okay, rather what we can then look at is the relationship between, because the moment I have two oxygens, my electronegativity is 0 because they got it from each other. And now when I get an extra oxygen, so an O3, then I'm on a 2 negative again. Okay, so now again I have that same electronegativity that I have. I have one oxygen that's trying to get electrons, but part of his electronegativity is being satisfied by the other two. They have some, so it's covalent sharing, so they share some of it. Okay, so for example, this would rather look like this. I want one here and I want one there. Okay, so it's not as if O3 2 negative has the same electronegativity as O2 negative, because this one's electronegativity, he is 1 wanting 2. This is 2 wanting 1. Do you understand? So they have a lower electronegativity. So in terms of this one, its desire for electrons is partly satisfied by the oxygens and by the sulfurs. They share it, but it still has a high electronegativity because I'm not exactly sure what the structure of this one would be like, but it has a fairly high electronegativity or desire still for electrons. But the other thing that makes him big, that makes it easily able to take an electron from hydrogen, is the fact that it is a large molecule. Because, okay, look at this. We've got sulfur has a high electronegativity, oxygen has a high electronegativity, and its sulfur is fairly big, and oxygen is not big, but there's 4 of them. So as a molecule, as a polyatomic molecule, it's a large, very large molecule. 4 oxygens, so let's count all of the electrons. 4 times 8 is 24, to 32, sorry, plus 16 is 38. And it consists of molecules that in themselves, they have high electronegativity. So actually the strongest acid is hydrosulfuric acid. Okay. Now another strong acid would be, let's see, we're in the 4. You see, these in the 4 have high electronegativity as well as large molecule. So I suspect this one, if he's in a, I don't know what it is, I think it's beryllium, so that will be silicate or something. It's not silicate. I can't remember what this one is. It's not one we use often. But for example, phosphoric acid is another very strong acid, because he's got a relatively, okay, it's roughly the same, but the oxygen, he's got 4 oxygens, okay, and it starts making it a high electronegativity as well as a large molecule. Carbonate has carbon, which is a high electronegativity, but not high, but higher than hydrogen at least, and he's got 3, because he's in the T, he's got 3 oxygens, okay, he's got a smaller molecule, so he's not so big. So so if we had to write them in order, we would get H2SO4, H3PO4, HCO, how many do we have? HCO, H2CO3, that's also another one that is fairly low but still strong enough to be considered a strong acid, is is it 3? Yeah, I think it's 3. So if we look at the table, that's nitrogen, oxygen, but it's only got 3. So I think these, I don't really know, but I think these two are not bad. They're not very high, but they're not weak acids. Okay, and that's because the molecules start getting small. Cool, but they're still fairly strong acids. Okay, so that's one way, and this is then just common acids that you can try and remember that are strong acids, and anything combined with one of those 3 would also be considered a strong acid. All the others would be weak acids, okay, like H2S. That's can't remember. Sulfuric Acid. Hydrogen sulfide. Hydrogen sulfide. If you look at that, it's not a small molecule, but it doesn't have a large electronegativity compared to hydrogen. Okay. Just a word that I would bring your attention to, I think the word is diprotonic acids. I can't remember. They often mention it in a test, and I can't remember that now. It's not in the course, but just remember that di means 2 and tri means 3. So whether it's diprotonic or I can't remember what the name is. That would obviously refer to an acid like this one. It's one that can donate 2 protons and not just a single proton. Phosphoric acid would be a tri, if I've got it now correct, triprotonic acid. But it just refers to how many it can donate. So that is also something I've picked up in some of the exams. Okay, now just strong acids and strong bases.
Get anything more than 3?
No, because the moment you get to 4, it won't be. The moment you get to 4, it won't be. There is a 4. You can't get more than 4, obviously, because then it is because it's all about giving away your electrons. Okay? And I won't give away more than 4, because then I can rather get. So if I have 5, I won't give away 5, I'd rather get 3. Understand? So I could maybe give away 4, or I could get 4, that's uneven. But instead I'd rather share. If I have 4, I'd rather be in a covalent bond. So for example, CH4, methane. Methane carbon has 4 hydrogens. Very unlikely for this bond, this one to donate its hydrogens. Okay, it's simply not strong enough to take the electrons. It doesn't have a high enough desire, and he already has 4, or he only has 4. So he must take 1 from 4 hydrogens. So this would be a very weak acid. It won't dissociate at all. Okay, so strong bases. The strong bases are very easy. Strong bases would be hydroxide that was bonded to alkali metal. In other words, if we look at our periodic table, that is this first column would produce a strong base. Okay. So here you can see like lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium or beryllium hydroxide. These ones you'll see are in the second, okay, calcium and beryllium. Okay, so I suppose the first two columns, both of them would be strong because they are they are donating their electrons very easily. So remember, this is something that releases OH ions. Now how will I release an OH ion is if I can actually donate, and OH is a negative. So if I can actually donate my electron to the OH. And they want to give it away very badly. So the lower you actually go here, the more. But again, the problem is the lower I go, the bigger that it becomes, and the more difficult it is to give it away. So that is why sodium is one of the strongest. Sodium hydroxide is the strongest base because he has a very low desire for his electron. Lithium has a little bit bigger and is fairly small. You see, he only has 11 electrons. The moment I go up, yes, my desire for my electron is less, but I'm bigger. It's more difficult for me to give away something when I'm an electron when I'm bigger. So
it's much easier when you're small.
To give away electrons. The same as when I'm bigger, it's easier for me to get electrons. The bigger they are, the more difficult they give away the electrons. Okay, so that's what we'll define as a strong base. Now, what we could now also define is because we know now, and we looked yesterday at the reversible reactions, that we have an acid, for example, HCl, that is dissolved in an aqueous solution. Okay, and that produces hydrogen plus chlorine, and these ions are always in aqueous solutions. This is not just an example. Now, because it's a reversible reaction, there is an equilibrium. And when there's an equilibrium constant. So the equilibrium constant, since this is an acid, instead of call it the Kc value, we'll call it the Ka value. So the Ka value is the acid equilibrium constant, and we take the concentration of H plus times the concentration of chlorine divided by the concentration of hydrochloric acid. Now remember, for strong acids like this one, it will dissociate almost completely, which means that the concentration of the numerator will be large and of the denominator will be small. So a strong acid like this, his Ka value is often much greater than 1,000. 10 to the power of 3. Okay. So, water dissociates into hydrogen plus hydroxide. Okay? If it dissociates. Actually,
isn't water neutral? Why did you say water is
say again?
Isn't it water neutral?
Yeah.
But you just said associate with.
Yeah, you see, water can still dissociate. Okay, but very little. So water can donate hydrogen, or it can donate hydroxide. Depends on what it is reacting with. Okay, and so because of that, it becomes the standard of what is neutral, because it can be either one or the other. But whatever it is, it's a weak, that one. It's a very weak acid. It's a very weak base. And why is something weak? It dissociates little. It ionizes little, and that makes it. So in other words, in the ionization, the equilibrium is to the far left. Okay. I just want to show you here, if I put hydrochloric acid in water, okay, and we get something like this, notice now that it dissociates. There used to be no hydrogen ions and no chlorine ions, but now that it dissociates, now I have hydrogen and chlorine ions, and they're in the same ratio. So in other words, these two values should be the same. So I would have hydrogen plus values and chlorine values down. The chlorine values, the chlorine concentration will be the same as the hydrogen concentration. Okay? And no. Yeah, I wanted to write H. Let me actually skip that. Let me just quickly look at the water itself, when it ionizes, sorry, I couldn't understand where the problem is coming. When it ionizes, okay, remember this is not aqueous. This is not dissolved into water. It is itself water, so this is just liquid. Okay, but it ionizes into H plus and OH ions. Now, very, very little. Very, very little. So what happens now is that if I go and get its K, now since I know it's not an acid, okay, since it donates both protons and it donates hydroxide ions, it's not an acid, it's not a base. Okay, it becomes the definition of neutral elements. Does that make sense? So this becomes, so it doesn't have a Ka or Kw, Kb, it will become Kw, the K value for water. Okay, it's unique. Now for him, if we work that out, remember when we work out the K value, we only use it for aqueous and for gases. Now there's no gases in here, so I'm sorry, I shouldn't have used this. So we only have hydroxide, we only have products divided by 1, because in the denominator, the reactants, there's nothing. There's no aqueous solutions, there's no gases, so there's nothing. So this is then H2O to the power of 0, which is just 1. Okay, so it's just 1. So this is the formula for Kw. Now remember again that the K value is constant. It's always constant for reversible reactions, related to temperature. Now at standard temperatures, that's 20 degrees Celsius. I think so, or 25. Let's see. On the table.
You mean standard the room temperature?
Yeah, standard temperatures, is it 25?
Yeah.
It's supposed to be on here. It's not. Standard conditions, it's not standard conditions, it's not room condition, room temperature. Standard condition is a standard 20. At these temperatures, they've now done experiments, and they find that the Kw value is 10 to the power of negative 14 in experiments. Now at different temperatures, this value will change. Okay? Now if this is true, and you can see it's a very small number, and now we said if it's a small number, it's a weak, because it doesn't dissociate a lot. Okay, now if we do that, we find also that if water ionizes, for every one of these ions, there's one of these ions produced. So these two concentrations will be equal, isn't it? So in other words, if we know that the concentration of these two multiplied gives me that, then that means that it should be that hydrogen ion is 10 to the power of -7 and hydroxide ions is 10 to the power of -7. And this is now where pH comes in. This becomes the standard for pH, because what P represents in chemistry, P in chemistry is negative log. So if we take pH, we are taking the negative log of H plus ions. So the pH of water is taking the negative log of 10 to the power of -7. And this simplifies, if you use your calculator or your rules, you multiply the 7 and -7 in front, it becomes +7. Log of 10 is equal to 1. So your answer is 7. But, so water is the standard. So if we change the temperature, pH changes. So this is 7 is the neutral pH at 20 degrees. If I increase temperature, it now depends. Does water dissociate more or less? Okay, I don't know. I think that when we increase temperature, the pH is higher. It doesn't mean water becomes acidic. It means the standard of neutral changes. And now for an acid to be an acid, it needs to be above that neutral, below that neutral value. If it becomes, for a base to be a base, it must become, so if the pH is 7,2, the pH of water, neutral water is 7.2, then neutral is 7.2. Anything more than that is basic, everything less than that is acidic. Okay.
Yeah, but can I please ask, you said the pH of water, but you're using only H ion.
Yeah, because that I'm saying P is negative log. H is I'm taking the negative log of the hydrogen ions. And so for example, I could also have POH. So POH is negative log of OH. And for water, we will always find that these two are the same, even at the same temperature. The pH and the POH gives you the same values. And you will always find that that pH times POH is equal to 14. That's a standard. That's standard because we are always taking. So now what we do is we take our acids and our bases and we dissolve them and we throw acid and base in water. We put acid and base and they start dissociating. So what happens now, if I take a strong acid, hydrochloric acid, and I put it in water, so I've got hydrochloric acid plus H2O. Okay, it's a reversible reaction producing H plus ions, but now the H plus ions connects there, so it's H3O plus ions plus chlorine ions. Now this just represents, so in other words, if I know what the concentration of H3 plus is, I know it's the same as the concentration of H3O. Okay, there's not a difference, it's the same, it's just the hydroxide, actually the hydrogen bonds, not bonds, but it's counted with the water molecules, okay, and the chlorine ions. Now, if I do this, this is now, because it's being mixed in water, when I take the K value for this one, let's say I don't know yet whether it's Ka or I am now taking this times Cl, because both of these are AQ, AQ. And this time I do have a denominator. Okay, so I'm not dividing with 1 because these two will still be equal. So if I divide it with 1, I would still get 10 to the power of negative 14. Okay, but I'm not dividing with 1. I'm dividing with the concentration of HCl. Now the concentration of HCl is not 1, it's little. It's very little. Okay, so if I do this, we find that because in normal water, if normal water dissociated, we would have had already H plus ions. But now we have H plus ions also coming from so now I would have standard in water, the amount of ions that I would have been 10 to the power of negative 7. Okay. Now if I increase these ions, I would have more than 10. So in other words, any acid that I can add, if that acid is a strong enough acid to dissociate, in other words, ions, it will. Isn't it true that an acid is something that increases the concentration of hydrogen ions? So if I started in water with 10 to the power of negative 7, if I add an acid, I will have more than that. Okay, now so if I take the pH on both sides, remember pH is log of H. So I take the log on both sides, but so I take the log on this side as well, but I take the negative log, so it changes the sign. So that is why if I take the negative log, I now get that, and this is pH, the pH of an acid will be less than 7. This simplifies to 7. And the same with a base. For a base is something that increases the hydroxide ions. So if I work out the POH, okay, I'll find that POH, the OH standard is 10 to the power of negative 7. Okay, so if I now add a base, I'm increasing this concentration, okay, which means I will have more of these than 10 to the power of negative 7. So if I take POH, okay, I'm taking negative log of OH ions, hydroxide ions, and negative log. But remember, the moment in an inequality, when I take a negative, I must change the sign when I multiply with a negative. So I took logs on both sides and I took a negative log on both sides, so that's why it changes. So it's 10 to the power of negative 7. So in other words, POH is less than 7. But this is not pH. I still have to remember the standard is that pH times OH, POH is equal to 14. So if I take this side and I multiply with pH, no, let me rather do it like this. So POH is equal to 14 divided by pH. So if I substitute that in here, I get that 14 divided by pH. No. Sorry, I said it wrong before. pH plus pOH.
Oh,
Sorry,
yeah.
that is equal to 7. Yeah, it will make it 49. Yeah, that's true. So in other words, pOH is 14 minus pH. So I already know that pOH is less than 7. So in other words, 14 minus pH is less than 7. So pH is then, if I take the pH to that side and the 7 to this side, pH would be greater than 7. This was for a base. For a base, the pOH will be less than 7. For an acid, the pH will be less than 7. Okay, so that is where pH comes in. So here's something that I always misunderstood about pH. I always thought that the pH of a strong acid is small and the pH of a weak acid is closer to 7. That's not what pH is. pH measures the concentration of H plus. So even if I take a strong acid and mix it in water, if I take a little bit of strong acid in water, it will have few, the concentration of H plus will be little. So I will still be close to 7. I will be less than 7 because if I even put 1 drop of acid in, I've increased the H of a strong acid. I've increased the H, but not by so much. Now the more of that strong acid I put in, the more of the hydroxide ions, so the hydrogen ions gets donated, increasing the concentration of hydrogen ions. Does that make sense?
Are you saying that a strong acid diluted is a weak acid?
I'm saying, yes. Well, basically, no. An acid is something that donates protons.
Yes.
Okay. So a strong acid diluted makes a weak acidic solution. So in other words, pH is about solutions. It measures the concentration of this in a solution. So yes, if a strong acid diluted produces a weak solution, a weak acidic solution. And the more concentrated I make that solution, the lower the pH would be and the more acidic the solution would be. So in other words, if I work out the pH value of lemon juice, okay, I know that lemon juice is an acidic solution. It's not an acid. It contains a certain acid dissolved in water. The same with vinegar. Vinegar is not an acid. It's an acidic solution. And so I measure the pH of that, and it will tell me then what concentration of acidic of acid is in there. Does that make sense? Okay, and this I've spent hours and hours trying to figure out pH. I could just not figure it out, because my understanding has always been pH measures the strength of an acid. No, it measures the strength of an acidic solution or a basic solution. Okay, by measuring how many hydrogen ions there are. Okay. Good. Now,
But if you put a little drop of a strong acid into water, then it means you're like dissolving it. you're diluting it, so it's no longer that acid. Would it be?
It is. You now have an acidic solution. What does it mean when if I say I've got an acidic solution? If I've got a neutral solution, I've got the same number of hydrogens and hydroxides. The moment I drop an acid in there, I increase the number of, or the concentration of hydrogen. So now it becomes acidic because it has more hydrogens than hydroxides. Now, if it is a weak acid that I dropped in, the problem is a weak acid doesn't dissociate. Do you see? This only dissociates partly. So it does increase the hydrogen because it does dissociate, but it dissociates little. So one drop of a strong acid and one drop of a weak acid will have different pH when I measure it, even though I've put in the same amount of acid. The strong acid will donate more of its hydrogens than the weak acid will donate. Yeah.